Well, thanks very much, and thanks so much to the organizers for the invitation. It's great to be back here in Paris, as always. Let me mention that this is joint work with Ben Adcock, Vegard Antun, Alex Bastunis, Matt Colbrook, Clarice Poon, Francesco Renna, and Werner Vlacic. And I'll be talking about two subjects that may look on the surface like completely disconnect, but there's actually a deep connection, which I'm going to get to at the very end. But I'm going to start with linear programming. And I'm going to talk about linear programming because this is a completely basic problem that we're working with in modern mathematics of information, and is one of the most investigated computational problems in the last half century. And you all know it extremely well. What I would like to point out, so here it is, but what I would like to point out is that with mathematics of information, we have become more demanding. We are now interested in minimizers. Now, classical optimization is really about computing the objective function. And typically, because in, say, operational research, that objective function, in many cases, has a physical meaning, like energy or time that you would like to minimize. In compressed sensing, for example, that objective function would be the L1 norm of the wavelet coefficients of an image. Completely non-physical, completely non-interesting. And we're interested in the minimizers. So I'm going to ask a simple question. How do we compute minimizers of linear programs? Well, we could try MATLAB, right? MATLAB has a built-in, very nice linprog command. The linprog command also has a very nice feature. It has an exit flag. And the exit flag will tell you if you're doing OK, and there's tons of things that could go wrong. Right now, I'm just interested in things that should go in the right way. So I'm simply going to try linprog on this very innocent little linear program. I have A here, it's a 1 by 2. I just assume people understand MATLAB notation. I have a very innocent little 1 by 2 matrix, which I'm going to change that value a little bit. Here's my y, that just becomes a number now since I have a 1 by 2 system. And here's the vector c. And I'm going to run it, and I'm going to see what MATLAB does. Now, in the beginning, I'm doing pretty well. I have 10 digits. And then at the end, I get complete garbage. I don't even get 1 digit. But on the other hand, that's where you have the exit flag, right? Because that exit flag is going to tell you that, well, there's things going on, except that the exit flag certifies the nonsense as completely correct. Not only does MATLAB give me wrong answers, it's actually very convinced that this is correct. Wow, what's going on? MATLAB is supposed to be trustworthy, isn't it? Well, I'm starting with linear program because you know it. But of course, in mathematics of information, there's a whole bunch of other optimization problems. There's a whole list of key optimization problems that we work with on a daily basis. Linear programming is just a start. You can talk about semi-definite programming, basis pursuit, unconstrained lasso, constrained lasso. And with the exception of the task of training neural network, these essentially form the basis of computational problems that we solve in daily basis in mathematics of information. Now, my innocent little question is, do there exist algorithms that can compute minimizers to these problems? And you go like, duh, it's the whole field of optimization. But, mind you, most of optimization is actually focusing on computing the objective function, and I'm asking about the minimizers. Moreover, I also want to make sure that this works in practice. And what that means is that I must be able to deal with approximate input. And simply because I'm going to be working with things like the discrete Fourier transform, discrete cosine transform, discrete wavelet transform, literally on a daily basis, those have numbers that are irrational. So I may have to approximate them. I could have, you know, the number √2 or cosine 3 or pi in my input. I will never know that. I can get it to arbitrary precision, indeed, but I will never know all the decimals of pi. Even if you are running strictly with rational numbers, like 1 over 3, well, if you're running floats, which you will be in 99.9% of the cases, that number is going to be approximated in base 2. Hence, what we're doing on a daily basis is always approximate. Now, of course, I'm not the first person to point this out. Steve Smale, even, in his list of problems for the mathematical problems for the 21st century, points out that but real number computation and algorithms which work only in exact arithmetic can offer only limited understanding. Models which process approximate inputs and which permit round-off computations are called for, indeed. And Laszlo Lovász points out that perhaps the most successful tool in economics and operations research is linear programming, which lives on the boundary of discrete and continuous. Indeed, there are combinatorial optimization problems that even deal with integers, but if you're going to do research in, say, economics, physics, and certainly mathematics of information, you will be working over the continuum typically with real numbers, and hence we need the continuous model. So here is the question that I'm asking, a little more formal. Take any of the problems on that list. Let's think about linear programs, because we know that well. My input is now given with some inaccuracy. I'm going to call that inaccuracy epsilon hat. And the question is simply, does there exist an algorithm that can compute an approximate solution so that the output of the algorithm is going to be guaranteed to be epsilon away from a true solution? And the whole point is that algorithm should be able to choose this input epsilon, the input accuracy freely as it wants. So from a practical point of view, what I'm asking, if you have linear programs, can you write up a code in MATLAB and you can use the variable precision command as freely as you want? And if I want 5 digits on my output, well, it should halt and give me that. If I get need 8 digits, yes, it should give me that. And if I need, say, 79 digits on my input, fine, as long as the algorithm can do that. And now we're really back to the foundations. Because if the answer to this question here is no, this is what Turing defined to be non-computable. This is from Turing's famous paper in 1936. Turing, being a very smart guy, deemed these issues non-computable because if the answer to that question is no, the following will happen. There will be inputs so that your algorithm is going to run for arbitrarily long time, say 50 billion years, and you still won't have been able to find a solution. Moreover, the algorithm will never know when to halt. So it could be that you iterate and iterate and iterate, and in the 50 billion plus 1 year, you actually reach something, but you will never know. The algorithm will never know, you will never know. Now, there's an issue here. If things break down, and suppose you couldn't get this to, say, 4 digits, it's very different from being able to say you can't do this for 16 digits, but you can get 15. That's why we define this concept of a breakdown epsilon. This is the largest epsilon for which all algorithms will break down. No algorithm can do better than that. And you may ask, do problems like that exist? Are there actually problems for which you can never get, say, 4 digits? Well, you're going to see. There are people here I know who are very, very good at numerical analysis. And the first thing that will come to your mind is that this must be related to condition. That's why we're doing condition. That's the whole point, right? In particular, well-conditioned problems should be fine. Ill-conditioned problems could be bad, right? So there's a whole myriad of different definitions of condition numbers in optimization. The first one is the condition number of a matrix, for which you all know very well, of course. Now, in a linear program, your matrix may not be invertible, but A star could be invertible. So I could talk about the condition number of that. I could talk about the condition number of the mapping itself. Say a linear program takes in an input and spits out a minimizer. That's a mapping. You can define, this is a standard definition of the condition number of a nonlinear mapping. You've got to be a little careful because it's multi-valued, but this is completely standard. A third concept of condition is the feasibility primal condition number. You don't want to be in the situation where you take a tiny little perturbation and then suddenly you don't have feasibility anymore. So this is taken care of with the feasibility primal. If that's bounded, you're essentially good. So now I'm going to reiterate my question. And I'm simply going to ask, do algorithms exist for these computational problems when everything is well conditioned? Suppose that I even know the condition number. Suppose it's 2. And the answer to that question is no. And now you think I'm completely nuts. But this is just the beginning. Here is what's really going on. What this theorem tells you is the following. Take any of the problems on that list. Let's do linear programming because we all know it. What will happen is the following. Take an integer k greater than 2. Then there exists a class of inputs so that the following is true. Everything in that class is completely well-conditioned and bounded, and I even know the condition number. But no algorithm can produce k correct digits, not even a randomized. However, there does exist an algorithm that can produce k minus 1 digits, But any algorithm doing so will take arbitrarily long time, even in the randomized case. However, if you're a little less greedy and you ask for k minus 2 digits, you can do it. That's in P. You can do that fast. So what this tells you is that there are cases for which it's the same kind of input. It becomes impossible, difficult, and easy at the same time, depending on how many digits you want. So what it says is that you will have cases for which you can very, very quickly get to 4 digits. It will take you arbitrarily long time to get to 5. Nobody can get 6. And keep in mind the example that I showed you in the beginning. This is that theorem in practice. Now, the k greater than 2 here is simply because I want to do this k minus 1, k minus 2 thing. If I'm only interested in the first part here, I can make k be equal to 1. There exist cases for which no algorithm can even produce 1 digit for linear programs, exactly as I showed you that MATLAB breaks down. I just want to say a little bit, because this is completely on the foundational part. I'm not going to get into the proofs of this. This is a very long paper. It's more than 100 pages now. We're desperately trying to finish it. This is the mechanism. We call it the solvability complexity index hierarchy. This is developed before. I'm not going to get into that part, but this is really on the foundations issue. What I'm going to talk about now are essentially what kind of consequences. And one thing that I would like to point out is that I could ask this question about linear systems. That makes total sense, right? Now, can I actually compute solutions to linear systems? And the answer to that question is yes. And I don't even need to know the condition number of that, as long as I know that A is invertible. And now you say, this does not make any sense, because I can solve linear programs if I can solve linear systems. Think simplex. But here's the catch. The point is that you will not know if these linear systems are actually, that the matrix there is going to be invertible. So you can actually solve linear systems, but you cannot solve linear programs, which is a fascinating issue. And now, of course, you think that I'm completely nuts, because, shit, this is what we're doing on a daily basis, right? So why do things work? So the consequences are essentially this. So first of all, how can you trust the output of your algorithm? The second one, and this goes to practitioners, do you need to care? Is this pure math mumbo jumbo? I do a lot of pure math mumbo jumbo. Do you actually need to listen to this? The third one is, but why do actually things work? Because I'm not saying that things don't work. I'm saying that there's a very, very peculiar reasons for things to work. Right. Can you trust your algorithm? Well, we already tried MATLAB. MATLAB can't even give me 1 digit, and it certifies this as perfectly fine. This is the theorem in practice. The question here is, why does MATLAB not detect that I'm bad? I mean, I know what I'm doing. I know that I've given MATLAB a bad problem. The question is, why does MATLAB not detect that? Because I can do the following thing. I can give MATLAB a bad problem if I want to solve a linear system, like I've done here. This is a 2x2 thing, highly ill condition, 1 in the upper corner, a tiny little number close to machine precision at the lower corner. And without even me asking, it just essentially says here, Anders, you've been bad. Don't be bad. That's what it says. So why on earth can MATLAB not detect that? Is this because the people who are doing the implementation of linear programs in MathWorks are incompetent, but the people who are doing linear systems are really good? No. It is super subtle. I haven't presented this as a formal theorem. This is actually quite involved to show this. It's actually impossible to compute the exit flag for any of these problems. And in particular, it is strictly harder to compute the exit flag than actually computing the solution itself. And it's even so hard that even if you had an oracle for doing your linear program, you can't compute the exit flag. And I know that sounds completely bizarre, but this is actually true. And that means that not only can you not trust your algorithm, you can't detect if the algorithm made a mistake. So, what does this mean? I would like to get into the practical consequence of this. And I would like to address the issue between the methodological and algorithmic error. And I'm going to start by asking you a rhetorical question. How do you set the halting parameters in your code? Well, you can kick that back to me and say, well, Anders, how do you set the halting parameters in your code? right? I'm going to tell you how we do that. And I'm going to do that by showing you a very specific example from applications, okay? This is an MRI example. This is done at Cambridge University Hospital. It's even our guy in the scanner. This is what you will see. This is a 3D scan, head scan. It takes 15 minutes. And so you see just a slice through the brain here. And this is the standard resolution. This is 256 resolution. And this part here is just the enlarged part of that. And what we're saying is that we have a new method. You should do completely different sampling. You should solve a completely different problem at the end. In this case here, we end up solving basis pursuit with a package called SBGL1 with a noise parameter. And this gives us that. And then we're claiming and saying, you know, you should use our method because, well, look at the image, right? It's so much better than the standard one. And the point here is that this also takes 15 minutes of scan, right? And you're like, oh, okay, great. How can I claim that this new method is actually better? It could be the case that this here is implemented with a completely ridiculous algorithm that can't even get 1 digits. I just showed you an example how MATLAB can fail. How can I guarantee that this is correct? How did we halt? How did we guarantee that what you're seeing here is actually not caused by an algorithmic error? Seems reasonable. Here is our halting criteria. We tweak with the parameters until we think it looks good. That's our halting parameter, halting criteria. And I can tell you this embarrassing halting criteria because I have a theorem to support you can't do better. This is what we do. This is what everybody does. Well, with the exception that this is typically what we all do. We look, and typically before conferences, if it looks better than the competition, that's the one you keep, right? So this happens at any imaging conference you go to. There's a parallel session, right? And in session 1, researcher A is showing off his new method. In session 2, researcher B is showing off her new method. And of course, they compare and tweak the parameters. And of course, in session 1, researcher A is declaring victory. And in the other session, of course, there's the same comparison, but the conclusion is reversed. Have you ever experienced this? Yes. This is why, and this is because of this theorem. So it is not in any way clear how we can detect if this is an algorithmic error or a methodological error. That's why this is an issue for practitioners. So why do things work at all then? This is a mystery, and I'm going to try to tell you why. And I'm going to talk about complexity theory for non-computable problems, and this is so nuts and self-contradictory, but this is actually what's going on. So, some of you might be old enough to remember when linear programs was announced to be in P. That was a huge thing. It even reached the front page of the New York Times. Few things in mathematics end up on the front page of the New York Times. What does it say? Well, you can Google it. There's tons of algorithms now. Carmarker's algorithms was not the original one. But this is what it says. LP being in P is this precise statement. You can solve linear programs perfectly 100% correct in polynomial time, and here's the catch. The polynomial is in 2 variables. N, this is the number of variables in your linear program. L is the number of bits in your number representation, or the number of digits. Now plug in the number pi in your linear program. Well, then L is infinite. This is not very helpful. There's no discrepancy between this statement here and the impossibility results that I showed you. Because this says, if I have rational input, that's fine, I can solve it. I don't have rational inputs. And I'm not interested in L, I'm interested in K, where K is the number of correct digits that I can get from my algorithm. That's what I'm interested in. So the computational problem that we're interested in mathematics of information is not the LP, it's in P. It's this. I want K correct numbers of my solution. And then I'm asking, what's the smallest runtime that I need to do to get K correct digits given N variables? And here's a delicate issue. I just showed you examples where this breakdown epsilon was greater than 0. And if that K is greater than log of that breakdown epsilon, no algorithm can do this. Yes, shoot.
Everything you're talking about is over the continuous numbers?
Yes. So,
rational numbers, everything works?
Well, not on all the other problems, but on linear programs, yes. So you can run simplex, and if you implement it, so actually the first example I showed you with MATLAB is due to round-off. It's due to the impreciseness on the round. If you implemented that with interval arithmetic with simplex, you would solve it. The whole problem is that I never work with this. I always work with floats, and I always work with real numbers, or things like a discrete cosine or discrete Fourier transform. For the other problems, even if you could do this, say, with lasso, that doesn't mean that, but for linear programs, you can solve this exactly, because that is a combinatorial optimization problem. So the key thing now is that if k is smaller than that log, breakdown epsilon, you may not be able to do this fast, but you may also be able to do it. There will be cases for which you can actually solve this in polynomial in n and k, and those are the cases we like, and a lot of those cases are actually there. For example, in compressed sensing. If you've never heard about these concepts before, completely fine. The robust null space property is a key property in compressed sensing. And the key part is that if you have this property of your matrix, you can recover S-sparse vectors. So in other words, if you could solve this, and by solve, I mean getting a minimizer, then you can actually recover here up to this noise parameter. So if you didn't have any noise, you can actually recover perfectly. So it's a legitimate question to ask. With all these extra assumptions, this robust null space property is a very strong assumption. Can I then actually compute minimizers to this problem? I mean, that's what the whole gospel of compressed sensing is. And the answer to that is a little bittersweet, but it's more sweet than bitter. Even if you have the robust null space property, you cannot compute this to arbitrary accuracy. But this breakdown epsilon, where everything breaks down, we don't know exactly what it is, but it's in this interval here, and it's proportional to the noise parameter. So if you look about here, it's off just by a factor of 2. And that means that your algorithmic error is not going to be worse than the noise. You can never get arbitrary accuracy. And if you see this is a practice. If you ever implement compressed sensing, what happens? You get very, very quickly down to 4 digits, and then it starts spinning. You can do this. You can try Chambold-Pock on this. You can try Nesta, SPGL1, or you do this on Lasso. Exactly the same phenomenon. This is what's going on. But it doesn't actually hurt you, because it is here. So, and moreover, the nice thing, you can do this quickly. So, the good thing is that, yes, you can actually do this, but in very, very specific cases. So compressed sensing is one of those. Okay, so what about this now? We're going back to the algorithmic versus methodological error. I didn't say how this is computed. This is simply the inverse f of t. So I simply apply f of t. So this is, with all the round-off, very close to precision, at least 10 digits. This one here, you can never get that to 10 digits. But with high probability, the breakdown epsilon of this one here is not worse than 4 digits. And 4 digits for imaging is completely fine. You won't be able to see any difference with a human eye if you change the accuracy in the 4th digits. So yes, this case here, this is actually better than that. And what you see here is actually very close to an oracle. There isn't any algorithmic error. Right, so that was the first part of the talk, and now we're going to change topics completely, but there is actually a deep connection at the very end. And now we're going to be talking about instabilities in deep learning. I'm not going to talk about neural networks and details yada yada on that, because there's been so many great talks before me, and you know these things very well. Just a little bit of notation. N stands for neural networks. The capital N here is simply this vector of dimensions that I'm going to have on my mappings. And when I talk about a neural network, I simply talk about a bunch of affine mappings connected with some nonlinearity in between. And I'm not going to talk about the great success of neural networks in classification. Everybody knows that. What I'm going to talk about is that they are completely unstable. And there's tons of work on this now. One of my favorite ones is the software called DeepFool, which is a part of the Foolbox, which is now a collection of all these softwares that shows how incredibly unstable deep learning becomes for the classification problem. I really highly recommend this paper here, written by these very fine researchers at EPFL, with this somewhat not a describing title. It's on the robustness of deep networks, but it's actually about all the instabilities. Highly recommend it. What they typically show is that take any great neural network that does extremely well on classification, there will always exist tiny little perturbations which are not visible to the human eye, and the network fails. This is a typical example. What you see here are the actual perturbed images. So the networks will actually recover this here as a sock, this as a dog, and then they add a tiny little perturbation, and what you see here now is the image with that perturbation. And then suddenly the sock becomes the Indian elephant, and the dog becomes the elephant, and well, you see the whole point. This is one of the greatest problems now in foundations of deep learning, because nobody knows how to solve the instability issue. And a good sign that this has become mainstream is now it has reached the press. So if you read the New York Times, the Guardian, or the BBC, and you look at articles on deep learning or artificial intelligence, a year ago it was always, oh, artificial intelligence is now revolutionizing this and that and blah. Suddenly now we essentially say, whoops, computers can be made to see a turtle as a gun or a concerto as someone's voice. So this happened not just in image classification, but also speech recognition. And this is a very serious issue. So there's not a lot of math behind this. This is a big mystery, and nobody knows how to solve this. All the existing neural networks out there become unstable. So we have cooked up a theorem just to show that actually stability is something that you should not expect at all. In fact, to the contrary. There's uncountably many cases of classifications, of questions a la, is there a cat in the image, for which you'll have the following phenomenon. Take any dimensions of your neural network. Choose an epsilon. That epsilon can be arbitrarily small, as long as it's less than 1 over k plus m. K is going to be the size of your training set. M is going to be the size of your test set. M can be arbitrarily large. Then there are even uncountably many cases of training samples and test cases for which you will have the following phenomenon. If you now train your neural network with your cost function, what you will have is that you will have 100% success rate on the training and the test examples. And mind you, the test can be arbitrarily large. But you will have uncountably many cases for which the network is going to fail, and it's going to be epsilon away even from the training set. And that epsilon could have been chosen arbitrarily small. Uncountably many cases for which this is going to happen. That's actually not the paradox. The paradox is this. There does exist another neural network for which is successful and stable. But that guy is not the trained one, and that is not constructed. It just exists. I don't know how to get there. And this is where Turing would haunt us, and he would have, if he was here, he would ask us, do you know if it's recursive? Recursive means, does there exist an algorithm that can actually get it? So the point here is that the trained neural network that you're going to get is going to be arbitrarily unstable, but that is actually not a fault of the class of neural networks. There does exist a good guy. We don't know how to get it. So now I'm going to get to the question about deep learning and inverse problems. There's been some very nice talks already. So I'm just going to do a very, very quick recap of this. It started with denoising. Simply, you have a bad image, and you would like to train a neural network to give you a good image from a bad image. Very simple. That's what people started doing. It's a little difficult, so one ended up essentially trying to learn the noise and subtract the noise from the image and then get a good image, right? But this you can apply in inverse problems as well. Suppose I'm doing MRI, and if I do MRI with subsampling, say I sample at 25%, I just set everything to 0, do my adjoint, put it back, get a crappy image. Well, could I train a network to give me a good image from a bad image? This is what started the whole thing of deep learning in inverse problems. And I'm asking this somewhat innocent question, but I think it's legitimate, given that one of the major applications where deep learning has success, namely classification, you see enormous instabilities. And the question is, will deep learning be unstable for inverse problems? So what we've done is that we've created algorithms to detect instabilities and software that does this. And I'm going to show you a test. This is a very, very high-performing neural network for MRI. And the reason why we've chosen this is because if you know MRI, you'll recognize some of these names here as big fishes in the field. These are actual practitioners. This is done at Imperial College London. What you have here is the original image. And What is done here is that is the patient, goes into the MRI machine. The MRI machine takes 20% subsamples of this, so speed up of 4. And then they've trained a neural network that takes the Fourier coefficients and map this and gives you this fantastic reconstruction. The question is it stable? What the algorithm does now is that it searches for perturbations here, and now we're going to see the effect on this side. Here are the perturbations. See if you can spot them with your eye, and here's what happens. In fact, I can deform that image completely by taking tiny little perturbations here that are almost invisible to the human eye. It's ridiculously unstable. Not only that, this is the important part. Look at the first part here. Suddenly I'm getting tiny little artifacts here. When you show this to radiologists, you go like, oh shit. It is not clear if you can actually verify this as non-physical. You have a whole continuum from this to, deforming the image completely with this. And the question is, how do you know if this is caused by an instability, or is this actually, blood in the liver, if you will, on this part here? Here's another one. This is a neural network that was actually published in Nature, and I want to comment on that. If you look at sort of what happened with compressed sensing had a reasonable big impact on inverse problems. There was never, ever a successful attempt in Nature to talk about image reconstruction with compressed sensing. This shows the avalanche that we have now and the enormous momentum there is on deep learning and inverse problems. You actually reach Nature with this. I highly recommend you to read this paper. The paper makes very, very grand claims that they beat everything, all state of the art, and they claim that it's more robust as well. We've tested this. This is 60% sampling, subsampling. It's still MRI. Here is the original image, and this is the reconstruction. The network is called AutoMap. We run the software on this one here to see what happens. Here are the perturbations. And by the way, we've added, actually, the patient doesn't have this heart. It doesn't have a tattooed heart inside. This is a detail that we've deliberately put there to see how it gets completely washed out. Check this out. It's ridiculously unstable. And in fact, this is just the tip of the iceberg. We have tested so many neural networks on so many different cases, and you can ask the question, do there exist stable neural networks that are trained? Yes, and they're crap. The ones that perform well are ridiculously unstable. In fact, training encourages the instability, and this is a major issue. So I encourage everybody, when this software will be available online, try it on your neural networks to see if you detect the instabilities and see how severe they are. So we have the fundamental problem in deep learning on the classification problem, which is simply, do there exist stable neural network for the classification problem? Well, I'm going to ask now, do there exist stable neural network for the inverse problem? And the point here is that I'm not happy with just the word exists. I need it to be recursive, because if Turing was here today, he would ask, can you find an algorithm that can compute it? Because existence theorems in pure maths are beautiful, but it doesn't help me if you're a practitioner. Okay. So what I'm simply asking is, can you find a recursive way to design neural networks that are stable for MRI, for example? And we call these things recursively adaptive neural networks, because we're going to let the architecture and the network to itself depend on the input. That gives us more freedom. The point is that we want to have a recursive mapping here so that I can apply phi of y to y. That's going to be the set of measurements. And I want that to perform well, and I want it to be stable. And the question is, do these things exist? To be able to show that what you can do about this, I have to go into a little bit of theory from compressed sensing. This is the concept of sparsity in levels. It simply comes from the fact that images are not sparse, they're sparse in levels, typically in xlets, simply from the constructions. You can look at the wavelet decomposition of an image, and you look at the different levels there, and you have different sparsities, different set of important coefficients. So this is what sparsity in levels encompasses. And that means that typically you have this SM term approximation, which means that you approximate your vector with something which is SM sparse, and you see how close you can get to that. There's another part, which is what we call multi-level sampling, which is also used in compressed sensing. And the key part here is that there is no such thing as a free lunch. You have to sample in a reasonable way. If you do completely moronic sampling, you won't be able to do anything. So there has to be a reasonable way to do the sampling. And typically what you do is that you align this kind of sampling with sparsity structures of images. Anyway. It's possible to make this rigorous. And of course, with a math theorem, which is rigorous, then there's a lot of detail, so it looks complicated. What it says is that, yes, I can find a recursive neural network, and I'm going to let the number of layers also depend on the noise parameter. This is very important. Typically, trained neural networks do not do that. We let that depend on the noise parameter. I can create a recursive neural network with the following properties. Here's the inverse problem that I'm going to solve. This is a discrete Fourier problem. It's a discrete MRI problem. This is a discrete Fourier transform. I'm going to sample with this multi-level sampling according to these rules here. A little complicated. I have a noise parameter. If I now apply my neural network with high probability, I'm going to be able to have both recovery guarantees here and stability. This is a neural network which is not trained, completely constructed. And then you say, well, okay, that looks good, but we all know pure math does not always align with applied math. There could be a hidden constant here that could be 10 to the 80, right? So you're asking, does it do things? Can it actually solve problems? Whoa. I don't know if I did something wrong, or was this a sign from somebody above? Pardon me? You pissed off Facebook. Oh, I pissed off Facebook. Right. Terribly sorry. Right. We have chosen to compare with the neural network from nature, given that they make grand claims. Here is the example that I ran before. This is the recursively adaptive neural network. And it is stable, as promised, and it performs reasonably well. I don't say that you are not going to do training. But we have to do it in a clever way, because the way we do training now will actually encourage the instabilities. I just want to point out that another problem when you do training is that your results will depend on your training set. If I throw in now an image of a Formula 1 car instead of these medical images, then the automatic network doesn't work very well. And they don't claim that it should. I'm just pointing out that this is an issue. Whereas this one here, which is purely constructive, there's no training, actually has no problem with this, which is described by the theorem here, because the only thing here is essentially the sparsity part. Now, I promised you that there was a link, because so far I've been talking about two completely disconnected issues. So where on earth is the link? And I have to tell you, the way we got into this was simply completely through the back door. We were interested in the foundational issues of how to actually compute problems in optimization. When we proved that, then we figured, aha, this is what's going on. And by adding these together, understanding this issue of the breakdown epsilon, then we can construct these neural networks. So on the surface, completely disconnected. If you really go into the mathematics behind this, there is a very nice connection. Right, I'm going to finish with this slide here, which is on validation and stability of deep learning. Because I'm not saying that we shouldn't do learning, and I don't claim that what I suggested here cannot be beaten, but we have to be careful. And I also don't claim that you shouldn't use unstable neural network. I just say that we have to make sure that we know how to validate it. So the second you show the existence of these instabilities, the question becomes, are they rare? Can you detect them? And can you actually verify if this is something bad, which is non-physical, or can you be fooled and get a false positive or false negative? Because this is a matter of life and death for a patient, you know. Are you going to operate on this patient or are you not going to do it? So this is actually a subject which is discussed on this workshop, which I think might be of interest to many of you. Google it, it's open for registration. But I want to bring this question to everybody's attention because this is essentially where we are now. So the second we have essentially established the phenomenon of instabilities, the community has to decide, what do we do now? How do we test it? How do we perform empirical tests that can guarantee that things are okay? Because it could be the case that the kind of instabilities that we've constructed are worst case scenarios that you will see 1 in a billion times, right? But it could also happen that this happens much more often. And the question is that a risk that you will be willing to take? And what is essentially the chance? And what is the actual risk? And that's a question that I'm not going to answer, but this is for the whole community to dig into. And with that, I stop and thank you very much for your attention.
Is there any question in the audience? Okay. So, yeah, sure. Wait for me.
Thank you for your interesting talk. Have you tried, at the beginning of your talk, you make a test with MATLAB. Have you tried with Python or C++?
Absolutely, it's a very good question. So the theorem will tell you that regardless of the software we're using, it will happen. But you might have to change your example. It's actually a very good point. Let me actually address this. It's a very good point. The implementation that I used for my example in MATLAB is the 2014 implementation. If you do exactly the same kind of implementation now in the 2018, or is there a 2019 implementation? I don't know. If you try this here now on at least the 2014, it will succeed because it's a different implementation. But you do the following, you change that perturbation here to the other part, and it fails on all of them. So it's a very good point. If I change this to Python or whatever, it might be that that implementation works on this example here, and it doesn't say that there is one example that breaks all. It says that for any algorithm, there is an example that breaks it, which is a different statement. So if you come to me with another algorithm, I will be able to break it, but not maybe not with this exact example, but with something else. So it's a very good point. But the answer is, the theorem is there. There is no way that we can get around it.
Thank you.
Any other question? No? Okay, so I have one. Do you have an idea on how to fix this train neural networks to make them more stable instead of being constructive the way that you showed it for
So the one that I showed is just to show that there isn't anything wrong with neural networks, but they're not trained.
Yeah,
and
absolutely.
I'm not claiming that this is the way to go. I'm just saying that if somebody asks me, can I solve the instability issue for the decision problem? I can't. If I could, I would probably be a rich man. So this is the big thing. But you can solve it in inverse problems. And the important thing is that deep learning does not have any competition for the classification problem. All of the other competition would have 30% failure rate. But in inverse problems, there are competition. And that's the whole issue we have to discuss. So what is the best one? If somebody is able to solve this problem for the classification problem, that will be huge. I have no idea how to do it. But I know how to do this for the inverse problem. So I think there was a question up there.
Yeah, sure.
Yes, I have taught for many years inverse problems to my students, and one of the tests that I do very often when I give them an algorithm to implement is I give them a set of the data, ask them to have the solution, but when they give me the solution, I just perturb a little the data and ask them to find run again the algorithm and find the solution.
Exactly.
And very often they are surprised from the results that they found.
Indeed.
This is exactly the problem that you
So,
mentioned.
and it's a very good point because, traditionally in the theory of inverse problems, the whole issue of getting stability has been the key part. Instabilities is a complete no-no traditionally in the field. And I'm not suggesting that we should sort of dismiss these things, but we need to know what we're doing. That's the issue. So as and I'm not saying that there aren't other unstable algorithms out there. Yes.
Is there a probabilistic perspective to this which might, so that in probabilities
Absolutely.
you can control the probability
Absolutely.
of failure.
And this is great, because that's why I want to point at this question at the end, the validity of the. So suppose now I do MRI, right? Suppose that I could show that these bad perturbations would not be hit if I do it randomly. So I have random white noise typically on the measurements, right? But here's the problem. A patient's movement is not random. I'm implementing this with floats. Roundoff is not random. I'm doing this even on the GPU. With single precision. I take a root, suddenly I have only 4 digits. So even if the noise model is random, there are so many other factors that I could end up getting into. So you might be able to come up with a random model for this, but that might also not solve the problem because there are so many other factors. So I don't oppose having a statistical model. It would be great. It would give great insight to potentially avoid these issues. But the issue is that it will still have to be a statistical test that the radiologist gets this and says, I can actually solve this problem and say that this patient here is with very high probability, either sick or well. So I welcome the mathematical theory, but still it might be very difficult to solve.
Okay, so there are 2 questions. We have to make a choice. And I think for the sake of time, we're going to defer the questions to the coffee break, right?
Yeah.
Okay. Thanks very much, Anders.
Thank you.